So for designing a simple processor, we will only need a few simple components, as in we are designing a very simple processor, so we'll start with very simple components. First will be memories. Memories are used for in terms of computer architecture, SoC processor to store either programs and data, or another way to say that is to store instructions and data. To keep things simple, we'll use a different memory for instructions and different memory for data. This is also the norm for real processors because we often want to access both instructions and data at the same time. So it's better to have separate memory for that in order to access that parallelly at the same time. Then we'll also have another component known as register file. A register file is simply a small multi-ported memory. It's basically memory. It's slightly faster than accessing RAM, and which we'll talk about. So it's a register file is simply again a memory, but it's a smaller memory typically, and it's basically it can be accessed using multiple ports. By multiple ports, I mean you can read two addresses at the same time, or more than two, or you can write multiple addresses at the same time. Instructions will read their operands, what data to be read in, those kind of things from the register file. In our example, what we are going to do is our register file has two read ports and single write port. So that means we can write two values at the same time and we can read two values and write a single value in a clock cycle. Other things which we have is registers, some additional registers, ALU, which is the core of your processing machine, adders, multipliers, depending upon what functions you want to do or logical functions you want to do, for example, shift, XOR, etc. And then the output of that is result. Then we'll have decode and control logic. Each of the assembly level instruction will be converted into a specific operation to be done, and that is done by your decode and control logic. Control logic will be more like if you want to do a jump, if you want to do a loop, those kind of things are enabled by control logic. Now, our processor, which we are going to design, the simple processor, can only load data from memory into our register file and store data from the register file into memory using special commands. Load, and these are known as load and store instructions. So basically, in our case, the processor, in case you want to read from memory, or in case you want to store with the memory, there are special instructions for that, which is known as at assembly level load and store. Architectures that restrict memory access to a few instructions like this are also known as load store architectures. Okay, so we cannot design a simple processor which will have memory, register files, ALU adders, logical operation functions, then there'll be decode and control logic. Our processor, which we are going to design, can load from memory into a register file and store data from register file to memory using special instructions known as load and store instructions. And this kind of architecture, as in which only allows writing to memory and reading from memory based upon special instructions, are also called load store architecture. Okay, so let's understand various parts of it. We little bit touched upon what are the various parts of it of a processor. We'll talk about little bit more detail. Registers. Okay, so registers or reg file are the smallest data holding elements that are built into the processor itself. So basically, you have processor CPU, and registers are kind of built into the processor itself. So it's kind of a memory, but it's a faster access memory because it's closer to CPU. Okay, and these are direct memory locations that are directly accessible by the processor. What can be in these registers is it may hold an instructions, it can also hold an address which you want to read, or sometimes it can hold directly data as well, or some other bit sequence as well, depending upon what operations you are, or your what instruction architecture set you have. So it can hold memory, it can hold data, it can hold addresses, but the thing is these are smallest data holding element is closest to the processor and directly accessible by the processor. Instruction may specify like content of two registers to be multiplied together, and maybe then the output result may be put there. Okay, so those are registers. Some examples of that is program counter, as basically which reads what is the next instructions to be read, what instruction registers. You can have address, you can have accumulate register. Let's say you're doing some multiplication and you want to save some data at the output, you can have multiplication register. So the register is one kind of memory element. Okay. Then the other kind of memory element is which is known as memory. Now, memory is a hardware device used to store computer program, instructions, and data. Typically, memory has multi-layered architecture. There'll be processor, and as we saw, there'll be registers closest to the processor. Then you'll have a primary memory, also known as primary cache. Then you have secondary memory known as secondary cache. Then you'll have main memory, and you can have additional secondary memory as well. So memory is a layered architecture. That is memory that is internal to the processor is a primary memory, and typical RAM. It's called random access memory. So basically, you can access it randomly. And it's there is also called DRAM, which is dynamically accessible, and you kind of have to dynamically charge it. Okay, but this memory is external to the processor. Then the other memory can be secondary memories. These can be hard drives if you know in your PC. So memory basically can be categorized in terms of how close they are to the processor. One is register file, one is your primary cache. This can be RAM. Your main memory or secondary memory can be hard disks. Memory can also you can also categorize memory in terms of volatile or non-volatile memory. What is the meaning of that is a volatile memory is a memory that loses its content when the computer or hardware device loses power. So if the hardware device loses power, like the power goes away, then the content of memory is gone. Okay. And random access memory or RAM is an example of volatile memory. It's closest to the CPU after registers and primary cache, but it's basically once the power is gone, that data is lost. Non-volatile memory is the memory if which it keeps content even if power gets lost. Your hard disk can be those memory. Your EPROM is also an example of non-volatile memory. So basically, these are memories that keep its content even if the power gets lost. So memory is basically more device used to store data, programs, instructions. And memory can be hierarchically understood in terms of how close they are to the processor, or also basically you can classify them into types of memory as well. Some high level differences between register and memory. Register holds operands, instructions that CPU is currently processing. Right now, what CPU is processing that should be closest to the CPU, and those are stored in the registers. Memory also hold instructions, data, and the program, but basically it may not be right now which your CPU is gonna use, but it's something which is gonna access. Maybe it's a big program, so you'll be converting that into instructions, and that will be loaded from a memory. But register file will contain what is CPU currently processing. Registers hold small amount of data around, maybe depending upon what kind of architecture it is. It can be 32-bit, it can be 64-bit, depending on what kind of architecture it is. Memory, on the other hand, on the computer or on an SoC can range from some gigabytes to terabytes. So it can hold large amount of data. CPU can operate on register contents at the rate of more than one operation in one clock cycle. So CPU access to registers, working on the rec file, CPU can do it very, very fast because it's very close to CPU and it's directly accessible. So you can access the register content at sometimes at a rate of much more than one clock cycle, whereas CPU access to memory is slower than access to a register. Some typical examples of registers are your program register, accumulator registers, instruction registers, address registers, etc. type of memories are RAM, DRAM, SRAM, DRAM, your EPROM, etc. Registers can be controlled, like registers can control the flow of the program. Like if your program has if loop, else loop, more in assembly like jump, loops, registers can control and basically store the information, and registers will have control information as always. Memory is usually not control based type of logic. Registers are faster than memory, and RAM is much slower than register in terms of access, both how you can access and how long it takes to get the data out. Okay. So now let's go into basically designing a simple 32-bit processor. And it's going to do simple instructions, but we'll do it step by step. So we'll assume all our instructions are encoded in 32 bits. So basically, whatever instructions we are going to give to the CPU, whether you want to do add, you want to do subtract, multiply, which two operands you want to do, basically all our instructions are coded in 32 bits. Our registers data path are also 32 bits. So basically what this means is you are telling CPU, let's say do multiply, but on what data you are multiplying, let's say A1 and A2 you are multiplying, those are also 32 bits. So that means our registers and data path are also 32 bits. Your memory is accessed with 32-bit address and returns 32-bit data on which we operate. And our processor, the processor, as we said, has a register file that also has 32 registers, each 32-bit. And so basically, in order to access this, basically we need 5 bits because 2 raised to power 5 is 32. So basically, in order to address our rec file, we need 5 bits. Okay. As in our data path in this case can be 64-bit wide, as in because the data path size and the instruction size encoding size need not be same. But basically our data, if you want, in our case, this case, our data path can be 64-bit wide also, and that does not mean we would need to change the width of our instructions. The instructions can still be encoded in 32 bits. Okay. So this just to avoid the confusion, since we are using everything as 32 bits, just to make sure, as in our data path for this can be still be 64 bits, while our instructions are encoded in 32 bits only. So this is our processor. Our instructions are coded in 32 bits. So we have registers and data path also encoded 32-bit wide. Memory is accessed with a 32-bit address and returns a 32-bit data. We have a register file which basically has 32 registers, so we can access it using 5 bits. Now, typically, right, in an assembly program or in directly CPU code, which is basically going to do some instructions, they're typically set of instructions. We are gonna go into a little bit more details as we go forward, but just to give a brief overview, typically operations which can be done inside on a CPU or ALU are basically can be written in form of what is known as basic instruction set. And these little bit detail will go into a little bit later in terms of instruction set architecture, but let's understand what kind of basic instructions can be. The instructions can be maybe add two operators and put the result somewhere, and subtract, or as we saw, right, in our case of load store architecture, basically load from memory, store into the memory, move from one location to another. Or there can be control structures like jump, loop, return, those kind of structure. So basically these are some basic set of instructions which are can be coded in assembly language. Of course, depending upon processor to processor, these commands will change. These, or what operations it can support, maybe some directly support multiply, some don't support multiply. Those kind of things can also change depending upon what you are basically ISA or instruction set architecture is. Now, for example, let's say a CPU, or you as you have, let's say you have a C level code which does this operation: x equal to y multiplied by y plus z. And let's assume x, y, z are stored in memory location 0, 1, and 2. So a typical assembly language code can be like move. Basically, this is what it's doing is move whatever is on address 1, move it to A. Whatever is in address 2, move it to B. Then basically you're doing this: add A and B, okay, and then store, and then multiply A and B, and whatever the results is, move to a particular location. Okay, so this basically normal code. Don't try to go into detail of this code, but basically any normal code C level code will convert it into this assembly code, and that assembly code is what your CPU is gonna execute, or your computer architecture system is gonna execute. And this is basic set of instructions for those, and this is what we are gonna design, that once you see these set of instructions, how is CPU gonna perform those instructions, or design at a at an RTL level or at a microarchitecture level, what this how these operations are going to take place. Okay, one another concept which is important is, and just I will briefly touch it, is what is known as code density. Code density loosely refers to basically how many microprocessor instructions it takes to perform a requested action, and how much space these instructions take up. Generally speaking, the less space an instructions takes and more work is done per instructions by a microprocessor, the more dense the code is. So basically, if per instructions it takes lesser space and more work a microprocessor can do, then code is known as dense. Typically, dense code have lower power requirement, so it's basically there's a lot of work which is done to make code dense, but that requires you to improve your instruction set architecture and also the compiler, and which we'll briefly touch upon. So for example, let's say you want to do a memory copy, which basically from particular set of addresses you want to copy, from a particular set of source addresses you want to copy to a particular set of destination. So this would be your C code, as in you have source, you have destination, and basically you will keep doing this source to destination, and then keep doing that. Now let's say if your instruction set architecture is simple, you will basically write this in a larger set of commands, which basically your instruction architecture supports. So usually you'll move the data, you will add the data, and there's some operation you will see whether count is zero or not. If count is zero, you will end the loop. So you can see, without going into too much detail, you have to do a lot of instructions here. If I count here, 1, 2, 3, 4, 5, 6, around 6 instructions are there. And so basically you have to do 6 instructions. Now let's say if uh, your processor supports multiple complex instructions as well, which is the case of, let's say ARM processor. This may be a simple, let's say MIPS processor. Then basically you will have loop, do something, and basically these are complex instructions. Not only this can do plus, this can also then store, okay, or subtract. Okay, so these you can see is done within the loop in 2 instructions. So basically you are able to do the same job with less number of instructions, and you are also taking less space, and more work is done per instructions, so this code is more dense. Denser code is important for power saving processor. Denser code allows you to save power because then you are accessing lesser, and basically it's doing more per instruction. And but just just because in this case, because your processor supports complex instructions, it's able to do that. But basically denser code can be a function of not only your processor able to do complex instructions and basically your efficient instruction set architecture, but it is also a function of underlying compiler engine. Okay, for example, let's say you have your C code, and if your compiler is not good, it can still convert that this code into this, even though architecture support this, instruction set architecture support this. So your compiler also plays an important role when you have a dense code. So both compiler and what instruction set architecture which exists, both play a good role in having your better code density, and is an important goal for power saving processors. So we briefly touched on it. We'll come to back to it a little bit in more detail. Now let's start designing a simple processor. First, we'll basically think of an instruction, and we saw some examples of an instruction. A simple data processing instruction in our processor can be simple. Okay, simple like this: what instruction you want to do, add, move, subtract, which we saw. Then basically destination, source, and second operand. Okay, now your second operand can be another, or maybe data something which is in memory. Maybe let's say you are doing x plus plus, and then basically your second operand can be just what is there in the memory, or your second, or you're doing x plus y, then the second operand comes from either immediate value or maybe a register. Now, given this, we have 32 bits to encode our instructions. So these are our instructions, sample format of our instructions, and we have 32 bits to encode our instructions. There are two simple instruction encoding formats which we can design. Okay, one format is basically this: some bit you give to operand, what operation you want to do. Then this is the address of your result. Then this is address of one operand, and this is address of another operand. If you remember, we had our basically instruction register file, which is 32 depth. So basically we are keeping 5 bit each for storing address of one result, address of your operand one, address of your operand two, and then you have function. So sometimes if let's say opcode is same, opcode decides, which is this, what operation you are going to do. Sometimes if opcode can be same, then additional information is given there in the function to basically do that operation. This is the case when basically two operands are different. If it's an immediate, we can basically have opcode result one operand, and then the second operand is in memory. Okay, please note this is 16-bit. Since our data size is 32-bit, this is only 16-bit. We can only do certain set of operations, plus as in we have to make sure as in this data is converted to 32-bit when the operations are done. So which we'll also design for. So this is when you're doing something immediately in the memory, but the data you can store immediately in our instruction set is just 16-bit. So that limits some things, and also you have to take care that it's converted to 32 bits when you're doing the operations. Okay, so these are two ways we can encode our instructions. Encoding is nothing but basically you're saying, okay, maybe for adding my code is 00, and let's say add on address 0, then the other address is 1, and store in address 2. So this is basically just giving information to the CPU that you read from this address one operand, you read from another address this operand, and then add it, because operation is add. So don't get confused about it. This is very basic. So basically this is how you can create an instruction set, which basically this will convert into this code and which will go to CPU.